Hi, this is Barrett Givens, and in this video, we're going to talk about this theorem that relates the closure of a set to its limit points, and we'll prove the theorem and talk about what the theorem means. So the theorem says, suppose you have a subset A of a topological space X, and let A prime denote the set of limit points of A. Then the closure of A is the union of A with its limit points. So another way to think of that is that if you want to form the closure of a set, you just have to take the set itself and then toss its limit points in as well, and then you will have the closure. Okay, so let's go ahead and prove this. We're proving that this identity, that something equals something, right? And both sides of this identity, these are both sets. So I'm proving that a set equals another set. And so I need to do the kind of proof when I try to prove that two sets are equal. One way of doing that is a subset style proof. So it really has two directions, even though it's not an if and only if, but it's a subset style proof. So my proof is going to have two parts to it. So one part will look like take an element on the left-hand side and show it must be an element on the right-hand side, and then the other part will be vice versa. Okay. So let's suppose that an element Y is an element of the closure of A. And we want to show that Y is either in A or it's in A prime, because we want to show that Y is in the union. So we want to show that Y is in A union A prime. And to show that something's in the union, you just have to show it's in either one or the other of the sets. Well, we don't know anything about this Y, so we have to think about two cases. So case one, sort of the trivial case. If Y is in A, then we are done. If Y is in A, then that's it. Then it's definitely in the union, so it's fine. Okay, so that was the easy case. Case two, if Y is not in A, and again, your cases have to be opposites. So since case one was Y is in A, case two has to just be the opposite of that, which is Y is not in A. So if Y is not in A, then, okay, what do we know about Y? We know it's in the closure of A. And we have the definition of the closure, and then we also had a theorem describing what kinds of points are in the closure. So let's try to think back about that theorem. That theorem talked about that Y is in the closure. If I took a set A and I had a Y that wasn't in A, it was in the closure if every open set containing that Y intersected with A. Then for every open set containing Y, and let's say open set U containing Y, U intersect A is not empty. That was a theorem that we had about if Y is in the closure, then this has to be true. Now, what do we need to prove that Y is a limit point? This is almost what we need to prove that Y is a limit point, right? What is the difference between the limit point and this statement? So the definition of limit point says that Y is a limit point of A if and only if for every open set U containing Y, U intersects A in a point other than Y. So this says that U intersects A, but it doesn't say in a point other than Y. Okay. So U intersect A is not empty, but that means it has some points in it. Could Y be that only point where they intersect? Well, no, because Y is not in A. So since Y is not in A, U intersect A must contain a point other than Y. Okay. So this point that we would be looking at, it would be somewhere over in this region over here. There has to be some point in there. And we know that it has to be a point other than Y itself because Y is not inside of A in this case. And so that means that Y is a limit point of A. So Y is in A prime, the set of limit points, because it is a limit point. So in case one, Y is in A. In case two, Y is in A prime. And so in all cases, it's in one or the other, okay? So in both cases, y is in A union A prime. Okay, because in case one, it's in the A part, and in case two, it's in the A prime part. It could be in both in case one, but for sure it's at least in A. All right, so that's one direction. That's one direction of this subset style proof. Now let's look at the other direction. Let y be in A union A prime. The meaning of union is that that means that y is in A or y is in A prime. And so again, we have cases because our hypothesis is an or statement. So we have to think about the two possible cases. So case one, y is in A. Well, we know that A is always a subset of the closure of A. So y would also be in the closure of A. Let's maybe draw this as well. So if I think of A as looking like this, then a closure is kind of like what you get when you sort of add in all of the edge points. And so one possibility is that y is already in A. Well, if y is already in A, then it's certainly in the closure because the closure is like bigger than A. All right. Now the second possibility, case two, y is in A prime. And the reason these are my two cases, again, is that I have this or statement right here that tells me it has to be one or the other. So those have to be the two cases that I would consider. Okay, so if y is in A prime, that means that y is a limit point of A. And intuitively speaking, we want to think of limit points as being sort of close to the set. Now, in some topologies, that definition of close might not really be close, but certainly like in the standard topology, I think we've seen from some examples that that is sort of the right way to think about it. So y is kind of like near A, okay? Y is sort of close to A. The definition of limit point says every open set U containing Y intersects A in a point other than Y. So if I were to draw an open set U containing Y, it would have to have some points in this region. And in fact, that point there, has to be at least one point there, and that point can't equal Y. It turns out here, it doesn't actually matter that it can't equal Y. What this means is that so for every open set U containing Y, U intersect A is not empty. I mean, it intersects A in a point other than Y. I don't even care if it's a point other than Y. I just know it intersects A. That's all I care about. So U intersect A is not empty. And therefore, Y is in the closure of A. So in both cases, in case one, if Y is in A, then Y is in the closure. And in case two, if Y is a limit point, then Y is in the closure. Okay? And I feel like this theorem sort of makes sense because if you think about it, if you look at the definition of a limit point and if you look at the theorem about the closure, they're almost the same definition, right? They're not exactly the same. They're different just in that one part about the intersection has to include a point other than the limit point itself. But other than that, they're actually really, really close, right? Like the definition or the theorem about closure says that a point is in the closure if and only if for every open set U containing Y, U intersect A is not empty. And then the definition of the limit point says every open set U containing Y intersects A in a point other than Y. Those are pretty close statements. They're very, very similar. And so it does sort of make sense that there would be a theorem relating these two things because it seems like they're awfully close to each other. Okay. So closure of A is not exactly the same as the limit points of A, but if you take the limit points of A along with A itself, then that is your closure. All right. And then we can have a corollary here as well. We have a corollary. Corollary. A set is closed if and only if it contains all of its limit points. Okay, and so that's a very useful corollary. That's a really good way to think about sets being closed. Why would that be a corollary of this theorem? Well, if we look at the statement of the theorem, it says closure of A is A union A prime. Now, if A contains all of its limit points, then that means A union A prime is just the same as A, right? If A prime, if all the limit points are already inside of A, then unioning with the limit points doesn't actually change A because they're already in there. So if A contains all its limit points, then the right-hand side, A union A prime, would just be A. And that would say that A was equal to closure of A. And we know that if a set is equal to its own closure, that the set is closed. All right. So that's kind of the brief why that is true. So this is actually a very, very important corollary. A set is closed if and only if it contains all of its limit points. Okay, thank you for listening.